This talk is about a weird machine which is created by memory deduplication, a feature offered by some virtual machine, some hypervisors, and lately also Windows 8.1 and higher. So it our paper presented at Security and Privacy yesterday explains the whole thing. So this will be a kind of an improvised talk with some extra thoughts about how this deduplication attack kind of fits into the how this relates to weird machines. So in our paper, the people, the authors of rowhanner.js have shown that it's now possible to use the rowhammer attack a hardware attack which allows for bit flipping in memory. That it also works from JavaScript, but the published attack using rowhammer to do privilege escalation is kind of difficult to do from JavaScript because it requires spraying of memory paging pages in memory. So it basically allocates lots of file-backed memory pages and then make sure a lot of pages in memory are actually used for the paging mechanism. So this is kind of difficult to achieve from JavaScript. So in our attack, we present a reliable, pretty reliable exploitation method to exploit Microsoft Edge from JavaScript using a memory leak that stems from the memory deduplication functionality in Windows 10. So in order to do our rowhammer attack, we need to leak some information. In this case, a heap pointer pointing to data we control, and a code pointer to the JavaScript library itself. And in our exploit, we pack this into a fake object, and then we will use rowhammer to flip a bit from a pointer from one fake object from one real object to our fake object, and from that we can achieve an arbitrary read-write primitive. So, but in order to leak this information, we'll be using a memory deduplication side channel attack. So, how does this work? In short, if an attacker wants to verify that a victim process or a virtual machine or anything has a certain specific picture of the Mona Lisa in his or her memory, then like this, then an attacker can replicate the memory pages, and then the memory deduplication mechanism in the OS or the hypervisor will identify that these pages are the same, and then will point the page tables to the same physical location. But then the problem is, if anyone wants to write to this page, you can't change it in the other process as well. So the page is marked copy on write. And that's where the problem lies, because this is detectable, and it's also detectable from JavaScript. Because if you change one page with a single write, it takes doesn't take a lot of time, certainly when the cache is not cold. But when you do this on a copy on write page, the kernel or the hypervisor has to do all kinds of stuff before you can write to the page. It has to deduplicate the page and before you can write to it, and this is measurable. So this is a neat trick, but all we can do is leak one bit of information, a confirmation that a certain page is in memory. So can we generalize this to leaking arbitrary data? So turns out in some cases you can, but there are some problems with this, because the secret you want to leak might not be the size of a page. So you need to have a way to encode a secret into a page. So the thing is that this is not really something an application developer should have to worry about, that you cannot you cannot create a page with a secret in there and then some other data that an attacker can guess. So it turns out you might have a socket and you write your data to the socket, and then it's written inside a buffer, but then you cut off just before the end of the page, and at the end of the page there's still some data you might want to leak. So this is not something an application developer should have to protect against. Then there's another problem, and that's that the thing you want to leak might have more entropy than you could probe for, because for every possibility you have to craft a page in your own memory, and then you will get the confirmation of which page exists in memory. But if you have, say, a pointer with 24-bit of entropy, you need 64 gigabytes of memory to probe for every possibility. So that's not really feasible. So there are some, in our paper we describe some ways of leaking this data anyway. So one thing is if you can control the alignment of the secret that you can you want to leak, you might be able to have a page with all known data, but with part of the secret you want to leak. So you only have to probe for part of the secret. If you don't control the alignment, there might be a different way of getting what you want, which is to overwrite part of the secret. In our exploit, we use the first primitive. So in Microsoft Edge, there's the JIT compiler creates machine code, but it has the last part of the function is always the same, except for the code address, and the code address carries some ASLR information, so we want to leak that. So by creating JavaScript objects, we can create pages which only carry part of the secret of the part of the ASLR information by having controlling the alignment such that the code address spans multiple pages, and then we can leak it in multiple phases and get the code address. But there might be a situation where an attacker cannot craft a page that where it kind of reduces the entropy of the secret it wants to leak. And this is the case for us. This was the case for us for the heap pointer that we wanted to leak. But there's another trick which is related to the birthday problem, which is the observation that giving a group of people the chances of someone having the same birthday as someone else in the group, for that is non-intuitively low. And the reason for this is that you're not comparing one person's birthday with a few other people's birthday. You're comparing every person's birthday with every other person's birthday. So in order to leak a heap pointer with data we control, we use the same principle. So we don't care which heap pointer we leak. We just want to leak one of them. So we just create lots of objects, and then and these objects represent and we make sure that we have pages in memory with references to these objects, and then we in JavaScript we can also create arbitrary binary data, and we guess references to objects, and then we use the binary deduplication mechanism of the OS to do an n times m comparison. It will, well, basically the whole mechanism of deduplication is basically compare everything with everything. So, well, that's what we abuse in this case, and we'll.
This is your weird instruction. Solve the paradox, solve the birthday paradox.
Yeah.
As those weird machines go, this one's pretty weird.
So, so basically, this is these slides are a demonstration of this. So, the chance of getting one hit so it's slightly different compared to the birthday problem because you have two groups, but the intuition is the same, and you only need the square root space complexity to get the right hit, get a hit. And then it gets deduplicated, and we can leak the address. So this is a figure from the paper I added. So in practice, we kind of have a side channel where we leak objects with on a megabyte boundary. So we kind of know the least significant bits, and then these objects represent pointers which are very close together, and then in our probe pages those are pages we guess might be in the address space. We take big jumps and then cover the whole address space, and then we get matches. So and recover the pointers that we are looking for. So to complete the attack, we now can create a fake object inside a JavaScript array. There's another JavaScript array which has a reference, a pointer to it, and then we need to change this pointer to our fake object. For that, we use the rowhanner primitive. In rowhanner, when you activate a certain row repeatedly, there's some physical properties of the DRAM memory which are made out of capacitors, which cause charges to leak, and if you do this quickly enough and you have bad memory, bits may flip. So using this bit flip, we can change flip, say, a 1 to a 0, and it will point to our fake object. And from that, we can escalate to arbitrary read-write. So the main thing to bring back is, I guess, that memory duplication is a bit more powerful than a 1-bit side channel, and yeah, rowhammer is browser exploitation using rowhammer is possible.